Hello, everyone. Thank you for watching the talk about our paper RusTEE. My name is Shengye Wan. I'm a PhD graduated from College of William and Mary. This paper collaborated with Minsheng from Baidu USA, Professor Sun and his student Xu from George Mason University, and Professor Zhang from Washington University in St. Louis. In summary, our paper provides a complete memory-safe SDK in the programming language Rust, and this SDK can contribute to developing reliable applications for ARM TrustZone architecture. Here is the outline of today's presentation. I will first introduce the background and motivation of our work. Then I will give an overview of our system, which covers the exact research problems we resolve for TrustZone applications. Later, I will present the implementation and the evaluation of the system. And finally, I will conclude our work as several takeaways. First, let me introduce some background knowledge and what motivated us to design the RusTEE. As we all know, today's mobile devices are facing multiple security challenges. On the one hand, every year, many new types of malware are identified and get spread out worldwide. Moreover, every year we can see many vulnerabilities are revealed to compromise the mobile OS, such as Android. Since mobile security is a serious concern, and most mobile devices are shipped with the chip that are based on ARM architecture, ARM officially provides its unique system-wide security solution named as TrustZone. As our work's background, ARM TrustZone technology can isolate all system resources, such as the CPU and memory, into two domains. The first domain, called normal world, is used to support daily applications and the rich OS like Android. Meanwhile, the secure world works as an isolated environment, and it only serves for security-sensitive tasks that are deployed as trusted applications. Under the ARM TrustZone threat model, the entire normal world is untrusted, which means the threat can spread from the application level through the hypervisor level. Meanwhile, by taking advantage of the hardware-assisted isolation, all the threats are believed to be restricted inside the normal world only. In this case, no matter how strong an attacker is, the normal world software cannot access any resource marked by secure world. Therefore, TrustZone can promise that applications inside the secure world, or so-called trusted applications, are safe from the normal world attacker. In the rest of the presentation, I will just use the word TA to refer to trusted applications. Though TrustZone can prevent any direct access from normal world to TA, recently more and more research reveal that TA are not safe enough as they are supposed to be. As a recent example, in Black Hat 2019, one CVE is proposed to compromise the entire secure world of Samsung S5. I list the pseudocode here to present how does this vulnerability is exploited. Basically, this vulnerable TA receives some untrusted parameters from the normal world, and then the TA uses them as the memory address without proper check. As the result, the TA is manipulated to copy the wrong data for the attacker. In our work, we focus on three specific security issues of TA. The first one is that many existing TA are written with the memory corruption bugs, especially for TA in C and assembly code. Though these languages provide a high efficient performance, using this language will have a high possibility to get an unrealized memory corruption. Second, most secure will deploy their system service with kernel privilege and further provide this service to TA. Because of this kernel privilege service, one vulnerable TA may affect the entire secure world. Last, recent years, several vulnerabilities prove that a normal world attacker can exploit the memory corruption inside the TA. The reason is that most commercial mobile devices allow the normal world to talk with the secure world via the cross-world communication. Originally, the cross-world communication is provided because some normal world applications also want to get the secure world support. However, nowadays, such communication also expands the attacking surface of the secure world. Here, we demonstrate the three issues with our previous TrustZone architecture figure. First, as we just mentioned, the TA may be buggy even if the developer is benign. Also, if the trusted OS provides any kernel privilege function to the TA while assuming the TA is benign, the bug may also make the secure world's kernel as vulnerable too. And finally, if there is any malicious attacker residing in the normal world, then she can utilize the cross-world communication to propagate its threat. As the worst result, we may have a fully compromised device that allows attacker to control everything on mobile. Now let's take a look on our design for solving these three issues. Our key idea is utilizing the memory-safe language Rust to assist the TA development. In summary, there are three distinguished advantages by using Rust. First, every Rust application is constrained by a language sandbox at the compilation stage, which means every lines of code are inspected as memory safe before they get compiled. Second, Rust has an efficient performance that is very close to C language. Third, Rust provides many libraries with the well-documented instructions, which can greatly increase the productivity inside the secure world. With the Rust memory safety benefit, we can promise the TA is free of most of memory corruption bugs and therefore resolve the first issue. By integrating Rust standard library into the TA development, most general data types and the basic control flows can be programmed in a memory-safe style. However, there's an implementation challenge for the integration, which is that none of the existing trusted OS is recognized by the Rust compiler. In this case, we need to prepare the trusted OS for supporting Rust standard library. So far, our work provides the support for two trusted OS of both ARM 32-bits and 64-bits architecture. Besides the standard tasks, a TA may still need to call some system service libraries, such as encryption, since these libraries may have legacy code base or dependencies on the assembly code. In most cases, C is still the better language compared to Rust. Normally, if a Rust program wants to invoke such C-based libraries, we need to bind the words of two languages via the Rust default mechanism, FFI. However, the mechanism is marked as unsafe because Rust cannot verify their security during the compilation. To further secure this C-based API, our project applies 6 principles to bind the C word and the Rust word, and the principles can be divided into 2 parts. The first part is proposed by a previous work, RusTSGX, which is a Rust-based mechanism that can compile programs for Intel SGX. In their work, 4 general principles are proposed to secure this C-based API, and they provide formal proofs for their principles. We apply all 4 principles for our SDK, but due to the time limitation, we will not cover these principles one by one. Besides these principles, we identified 2 specific principles for TrustZone scenario only. The first one is that one TrustZone system service may involve several API, and this API should get invoked in a fixed sequence, which is called serialization. Here is an example. The OS provides AES encryption as 3 separate steps, including preparation, encryption, and finalization. However, in the real-world development, a TA may invoke the encryption directly without preparation, and this mistake can lead to a failed encryption. Our mechanism promises all the serialized API will get invoked with the correct order. Another specific principle is that normally a trusted OS requires the TA to manually allocate and free the used data, but they are often forgotten by the developers. As the enhancement, we enforce all these allocation and free steps with Rust built-in features, so they get executed by default, and here is an example of our principle. Finally, we secure the cross-word communication channel for TA. Typically, a TA will talk to a normal world software with 4 data structures. After we review the design of these 4 structures, we noticed that a TA should strictly manage these structures' lifetimes, while the current API has no guarantee on this. Also, for the most tricky structure parameter, the existing design may get misused easily about the parameter's permission or data types. Our SDK mitigates these threats by utilizing the 3 distinguished features of Rust, namely lifetimes, mutability, and type safety. The details of this enhancement can be found in our paper or open source project. Now let's put our defense together. By enabling the Rust memory safety on TA, we are looking forward to have a TA without any known memory corruption bugs. Furthermore, since we secure the system API and the communication channel, even the attack exists in the normal world, the attacker cannot easily manipulate the TA to compromise the trusted OS. Now let me present some details about our implementation and evaluation. We implement a prototype of RusTEE based on the open source project OPT. OPT is a popular TrustZone trusted OS, and it already provides a C-based SDK for developing their TA. We apply all RusTEE design onto the OPT C-based SDK, and finally we build 13 Rust-based TA for the OPT. Among these examples, 6 are mirrored versions of OPT example, and we use them to compare the performance between C and Rust languages. The other 7 examples show that RusTEE can support most mainstream TEE use cases, such as encryption and secure file storage. We open sourced our project on GitHub, and the total involved lines of code are more than 8,000 lines now. Our project has been evaluated as ACM reusable by XA community, and you can refer to this link or our paper to locate our project on GitHub. Now let me present the performance comparison between RusTEE and the original OPT examples. Overall, RusTEE only introduced less than 1% overhead in average, and even the worst case incurs the overhead around 3%. We believe such overhead is acceptable, especially considering the extra security benefit we provide. Finally, I'm going to conclude this work. So for you to take away today, it is always good to have ARM TrustZone TEE as memory safe, and we believe Rust can contribute to build such TEs. Also, the trusted OS should be careful about any interaction with TEE. And finally, the TEE should use any normal world data very carefully, such as adopting RusTEE for help. That's all for my presentation today, and thank you for your time. Now, please ask if you have any question. Due to time conflicts, I will not be there for the QA session, and Mingsheng will be the one to answer your questions. Thank you.